Hello everyone! In this video we will continue to examine topic 12.2, nuclear physics, and in particular the law of radioactive decay and the decay constant. So, our final subtopic, our final thing that we're going to revisit from topic 7 is the idea of radioactive decay curves and the half-life. And some of this, you'll probably be best served simply by revisiting topic 7 and the relevant videos. But one of the things we now have the ability to do, as mentioned previously, is connect what we have said about the wave function to the calculation of lambda, the probability for it to eject a particular particle, for alpha decay, or really undergo a decay at all. We initially encountered lambda as the decay constant in our fundamental radioactive decay formula. Without going over all of the details again, remember that radioactive decay was the random and spontaneous emission of particles, or high-energy photons, from unstable nuclei as they decay from high-energy to low-energy states. And we can unpack this now in a little more detail as often involving a quantum tunneling event. It is fundamentally probabilistic in nature because quantum is fundamentally probabilistic in nature. And if a nuclide has a fixed probability of undergoing decay, then the rate of the total decays is proportional to the number of total nuclides. So that probabilistic nature from quantum mechanics then gives us this fundamental relationship here, which is that dN dt, or the rate of change of the original nuclide, is equal to negative times lambda, that decay constant, times n, where lambda is understood as the probability a particular nuclide will undergo a decay per second. And quantum mechanics allows us to derive this quantity in different scenarios. The rate of decay, dN dt, is also known as the activity, measured in becquerels. So, the only thing we're going to add to our analysis here is at HL you will be expected to handle discussions of radioactive decay and calculations in radioactive decay that involve more than simply integer half-lives. So 1 half-life, 2 half-lives, 3 half-lives, etc., which was what the requirement is at the core. I'm also going to spend just a little bit of time, for those of you with the math here, to show where this equation comes from. So dN dt equals negative lambda n, that is the rate of decay being proportional to the number of nuclei that are left in a particular sample, is a differential equation, and can be solved using techniques that are accessible usually at the end of SL math or at the sort of midpoint of HL math. And those are the techniques I'm going to discuss moving forwards. It is okay if you don't follow this. It won't be required to repeat it. But there is a fundamental connection between this differential equation and the solution to that differential equation, exponential decay. So, without further ado, if I start with this particular equation and I do something which bothers the mathematicians, you can ask them why, but I multiply by dt on both sides, and I divide by n on both sides. That gives me all of my n values on the left-hand side and all of my dt values on the right-hand side. You can think of this as the time side and this as the number of nuclei side. And then what I'm going to do with this differential equation is integrate both sides. And I'm integrating from particular bounds. I'm integrating from the moment and number of nuclei at 0 up to an arbitrary moment and number of nuclei at time t. So any old t I want, And those are my bounds. So I'm going to integrate the number of nuclei from n naught, that is the number of nuclei at the start, to n. And I'm going to integrate the time from 0, to the time at arbitrary time t. In doing so, the integral of dn over n is log okay, the natural logarithm of n over n naught, where n naught is a constant and n is a function of time. And if I integrate this side of the equation, the integral from 0 to t of any constant dt is just t, okay? Because as I substitute in my bounds, the 0 term drops away, and so I'm left with just t, the time, in my integral. I then solve for n as a function of t, and that gives me n naught e to the negative lambda t, okay, taking the exponent of both sides. And so this is the derivation of the equation governing exponential decay. Now, with that equation, we can also define the half-life as the time it takes for half the sample of nuclides to decay. So t sub 1/2 is equal to log of 2 over lambda, the decay constant. Where did this come from? Well, if we take this equation, we say, all right, well, the half-life is just when we reach half the original sample, and that's equal to n naught e to the negative lambda, and then we define that as t sub 1/2. Then we can solve this equation for t sub 1/2. Our n naughts cancel, and we get 1/2 equals e to the negative lambda t sub 1/2, and we solve for t sub 1/2. That gives us log 2 over lambda. Okay, log 2 over lambda. So this will be useful for any arbitrary thing. If you're given the half-life, you can then determine the rest of the equation. So you're given the half-life and the original number of nuclei. Notice that the half-life and the decay constant are interchangeable in terms of information. So if you're given lambda, you can get the half-life and vice versa. And then with those pieces of information, you can use the general equation n of t equals n naught e to negative lambda t to find the value of n at any particular point, okay? And that's the thing that HL adds that SL isn't required to do. So not just integer numbers of half-lives, but any arbitrary time, you can use this equation to solve for the number of nuclei left in the sample. We can also note that if we define the activity as the rate of decay with respect to time, dn dt equals a, where the unit is the becquerel, BQ. This is understood to be the number of decays per second. If n of t is n naught e to the negative lambda t, then the graph of activity will be the same. And just applying our relationship here, if a is just the time rate of change of n, so dn dt, then if I take a derivative of this particular function, the only thing that happens is that I get my constant to drop down, and so my initial activity is just lambda times n naught. Notice I do pick up a minus sign, but we almost always define the activity as being a positive quantity. It is understood that the activity means that the number of nuclei is decreasing. So it's simply understood in the definition of the activity that there is an implicit minus sign corresponding to the fact that the number of nuclei of the original sample, okay, of the parent nuclide, is decreasing. So in practice, all right, often the measurements of the activity are much easier than the measurements of the n for reasons we discussed in topic 7. If the half-life is very short, we measure the activity using a Geiger-Müller tube or Geiger-Müller counter rather than a mass spectrometer or the like to determine the isotopic ratio of the materials. So there's sort of two regimes. One is the half-life is very short, at which point we measure the activity in order to understand what is going on. The other is the half-life is very long, at which point we measure the isotopic ratio, or the ratio between the parent nuclide and the daughter nuclide at any given moment in time. Okay, so we're talking this equation and this situation is almost always more useful for things that happen on the scale of hundreds or thousands of years, and this scale is more useful for things that are more unstable, happening on the order of seconds, okay, and less than that.